We'll wait another minute. I hope you guys have no trouble signing in. You will have to use your CUHK ID to log into Zoom in order to participate in this class. Let me see. Okay. Good. I think we can get started. So welcome everyone to this Zoom meeting for the UGB2401G astronomy class. Unfortunately that we cannot have all the class in person in the classroom because of the COVID pandemic, but it's good that we can still continue the teaching and learning. So with Zoom, it will take some effort for both you and me to interact more on Zoom. So I encourage you all to ask me questions during my lecture. You can either raise your hand, you can type in the chat window, you can also just unmute yourself and speak up if you couldn't get my attention during in the middle of something, and you can just stop here any time so that I can explain something more if you have a question. The homework assignment has been assigned on Blackboard, and so I have changed it so that now you don't have to turn it in person anymore. You can turn in the homework assignment online through Blackboard. You just need to upload your answers to Blackboard. So you can type your answers in a document and then upload it, or you can actually type it directly on Blackboard, I think. For the office hours, if you want to attend my office hours, you now need to email me in advance so that I can stay on Zoom. I think I will just use the same link as this one and then wait for you in this on the Zoom meeting link. But if you don't email me, then I may not go online to wait there. For anything else, I think that's it. I'm going to, for the meeting, I'm going to turn, for the class, I'm going to turn on the focus mode. So I want to try that out a little bit so that I think in the focus mode, you only see myself. I just want to make sure that you can still type in the chat window. Can someone type something there, or can you still type in the chat window to ask questions during the focus mode? Yes, okay, good. I can still see your video, so you don't have to turn it off. I think it's in this mode, you guys cannot see each other and you can only see me. And so this is a good, that is a mode that is useful for you to focus on my lecture. Okay, I'm going to start sharing my screen so that we can get started. Where is full desktop? Can you see my slide?
Yes.
Okay, good, thank you. Good. So I can see the chat, and you can also raise your hand in the middle, and so that I can see that. So at the last lecture, we were talking about the motions in the sky, and there was a little bit that we didn't finish. So first of all, today we are going to finish that. I don't have any review questions for today. So I will start reviewing the content from last lecture. So last time we talked about the motions of objects in the sky, and we talked about what factors affect motions of stars in the sky. And we talked about the time of the day or the date in a year will affect what you see and or your latitude on Earth would affect what you see. And also the date in a year or the seasons would affect what stars you see in the sky. So, and that is because the Earth goes around the sun, and we can only see stars at night. So when it is at night on Earth, is that when we are on the side of the Earth that is facing away from the sun, we can see stars, right? The side of the Earth that facing the sun is during the day, the side facing away is at night, and at night we can see stars, so that if Earth is at this position on its orbit, we see stars in this direction. But if the Earth goes on another part of the orbit, it will see stars in that direction. So in different seasons, as the Earth goes around the sun, we will see different constellations. And the most notable constellations are the 12 constellations that lie along the ecliptic. The ecliptic is the apparent track of the sun in the sky as the Earth orbits the sun also moves relative to the stars from our perspective. So if we could see stars during the day, we would see the sun is actually is projected among the stars. And that position will go through different constellations during the year, and we call that track the ecliptic. It's basically a big circle on the celestial sphere. So the zodiac constellations are defined to be the constellations that the sun is in during each month. And so these are the 12 zodiac constellations, and you're all very familiar with it. And last time we used the Stellarium software, and we showed that where the sun is in each constellation in different months. And we also looked at what constellations you can see at night in several different months. And you found that if you see the sun is within a certain constellation during a certain month, then 6 months later, you would see that constellation at night. Because, for example, in September, you see the sun is in the constellation Leo. 6 months later, the Earth will go to this position on its orbit. So the 6 months later will be March. And if the Earth is at this position on its orbit, then we can see the Leo constellation at night. So whatever constellation you see at night is corresponding to the constellation that the sun would be in 6 months, in 6 months later, right? So I hope that is clear. I have no more question about that. So that the third factor of what determines what stars we see during the day. What stars we see in the sky, not during the day, of course. Time of the day changes that latitude on Earth would affect what stars we see. And also dating a year while Earth is on its orbit would change what stars we see. And there is actually a fourth factor. What else? What other factor can affect this? This factor is called precession. What is precession? Precession is describing a motion that a spinning top would have. So whenever you use a spinning top and trying to rotate it, you would notice that its axis is actually wobbling around as it spins. So I'm going to show you a demo on my desk. Hope that will work. Let me see. Let me stop sharing my screen. And now I hope, let me also turn off my virtual background. So I have a spinning top here. This I just made it myself. This is a toothpick with some papers, very simple, and you can see my desk, right? And if I just spin it, it will spin on the table. And I want you to pay attention to the axis and see what the axis is doing. You can see as it spins, the spinning speed is very fast, but the axis is actually wobbling around, right? And that is what we call precession. So you can see the axis is actually wobbling around, right? And that wobbling speed is actually slightly slower, somewhat slower than the spinning rate of the top. So now actually, let me go back to screen sharing. And there is another video, actually, I want to show you. So this is also a video of a spinning top. You can see there's a top here, and in the video, it will spin very quickly. And you can see that the top spins really, really quickly, but the axis actually wobbles around at a much slower rate. The reason it wobbles around is because of gravity of the Earth. And the reason that the spinning top I was showing you on my desk, the reason that axis, that rotation axis is wobbling around is also because the gravity of the Earth. Because there is a force dragging it down, and combining the rotational motion and the gravitational force, it causes the axis to wobble around slowly. Can you see the YouTube video smoothly? Okay, thank you. Thank you for the feedback in the chat window. Okay, so that is what we call precession. And the Earth actually have exactly the same effect because the Earth is, how do I get out of this? Let me go back to my slide. So now I'm showing my slide. So the Earth is actually doing the same thing. The Earth is spinning in space, and there is very strong gravitational force act on it from the sun. The sun is pulling the Earth in a certain direction, right? It's pulling it so that the Earth goes around the sun. And that gravitational force combined with the spinning motion of the Earth, it causes the rotation axis of the Earth to wobble around. But because the Earth spins not that fast, it only spins one round every 24 hours, right? So it's not as fast as our spinning top. That wobbling motion is also very, very slow. The wobbling motion actually has a period of 26,000 years. So actually every 260 centuries, it will wobble around for one period. So it's a very, very slow wobbling motion. So it's actually very difficult to notice. But over long periods of time, we can notice that. And that actually causes was a change in what stars we see in the sky. And first of all, what is the rotation axis of the Earth pointing at? Our rotation axis of the Earth is pointing towards the north celestial pole and south celestial pole, correct? Right? And so that we see the reason that Polaris, when you if you look at the reason that Polaris can be used to direct us towards the north is because that star is very close to the north celestial pole. It's very close to the point that our Earth's rotation axis points at. And because the rotation axis is actually wobbling around, which star is close to the north celestial pole actually changes. So here is a consequence of precession. Right now, we are at this time in history that the red cross, this is the point that is pointed at by the Earth's rotation axis. Polaris is very, very close to it. This is the North Star. And so that is why we call it North Star. It is almost stay fixed in the sky. It doesn't move very much. It moves around a very tiny circle around the north celestial pole. So it almost seems it is not moving. So that's why we use it to direct us towards the north so that we can use it to find directions. but because the rotation axis of the Earth is wobbling in space, it actually moves among the stars. So this is the track that is actually traced by the rotation axis of the Earth. In different years, it actually points at different place. So for example, in about 6,000 years, when it is 80,000, the rotation axis of the Earth will be at this position in the constellation Cepheus. And then in another 7,000 years, when it's 15,000, it will be close to the constellation Lyra or Vega. And then, and if you go back in history as well, so because this is a periodic motion, that if we go back for 7,000 years, this is 5,000 BC, this is where the rotation axis of the Earth is. So in different historical times, the rotation axis of the Earth is pointing at different constellations. And so this is going to cause what stars we see to change in the sky. So here is a task description. And this is also causing the solstice and equinoxes, and we'll talk about that in a little bit. So with the seasons will also change because of the wobbling motion of the Earth, because of the precession of the Earth. So the constellation at the spring equinox is also changes slowly over time. It's currently in Pisces. It's in about 700 years, it will be shifting to Aquarius. And this is the reason why last time that when we were using stellarium to check what constellations the sun is in different months. For example, we saw that on March 1st, the sun is in the constellation Aquarius, but actually according to the zodiac signs or the correspondence between birthdays and zodiac signs, Aquarius should be a February constellation, not a March constellation, right? So there is a shift, and that shift is actually due to this precession of the Earth. So here explains that originally your astrological signs, that is which month you were born, corresponding to what constellation, that was determined by the Babylonians in about 600 BC. That was 2,600 years ago. So remember, the period of the precession is 26,000 years. So about 2,600 years ago, at 600 BC, that was about 1/10 of this period. So that basically the position of the North Central Pole will move about 1/10 of that circle, and that is causing a shift in between the dates and the constellations. So in the correspondence between the calendar day and the sun was defined about 600 BC, but today it has shifted by almost 1 full constellation, by about a month. That is why that currently where the sun is in the sky when you were born doesn't really corresponding to your astrological signs according to the rules that set by the Babylonians. So that is why it has such a large shift that we found last time. And also something made the news recently is because now there is actually a 13th zodiac constellation. So this is what the astrology says, and this is the real dates currently, that you can see that it's shifted by really about a month. That, for example, Capricorn, it used to be assigned to these dates, but if you ask where the sun is in which constellation the sun is in, it is actually between January and February. It is in the constellation Capricorn. So this is a shift that I was talking about. In addition, there is now a 13th constellation that the sun is in, because the ecliptic track actually moves around slightly, and now there is the constellation of Futurus is also overlapping with the track of the sun in the sky. So people are surprised about that. So this made the news about 10 years ago in the media that people was thinking, wait, how can there be a 13th zodiac constellation? But you now know that the zodiac constellation really has nothing to do with your birthdays. It's just that the apparent position of the sun in the sky, and because the precession of the Earth, this can shift around, and then other constellations may also get into the track of the sun. Okay, any questions about this? So let me see. Wait. Sorry, somehow I lost my screen sharing. Any questions on these? No, we can continue. So what factors determine what stars we see in the sky? There are 4 factors: time of the day, latitude on Earth, dating a year, and precession of the Earth. So these are 4 factors determine what stars we see in the sky. So that concludes the section on the chapter on motions in the sky, motions of stars in the sky. Okay, now we are going to move to the 3rd chapter, in which we are going to talk about the reasons for seasons, the reasons for phases of the moon, and eclipses. I see there's a question. So question is, we want to confirm that it is only the gravitational force of the sun on the Earth and the rotation of the Earth that causes it to recess. That is correct, yes. So the precession is caused by the gravitational force of the sun on Earth and the rotation of the Earth. So any spinning things in a gravitational field, any spinning things under gravitational force will have a precession. Okay, so in this chapter, chapter 3, we are going to talk about what are the reasons for seasons and what are the reasons for the phases of the moon, and also what causes eclipses and what we need to learn about eclipses. So first, I want to ask you a question, and I want to make a poll on Zoom, and so that you can answer the question on Zoom. So please, now you should see a poll in the Zoom window. Please answer the poll. So why do we have seasons? Is it because the Earth is closer to the sun in summer and farther away in winter? Or is it because the tilt causing one hemisphere to be closer and the other hemisphere to be further? You can select multiple options. You don't have to select just one. Or is it the tilt causing the days to be longer? Okay, answer it if you haven't. So I see most of you answered chose the second one. Most of you chose that the tilt of the Earth. I actually, let me see. If I end the poll, do you see the results yourself? No, you don't see the results. Okay, so I'll tell you. 20% of you said A is correct, 80% said B is correct, 20% said C is correct, and 20% said D is correct. Of course, this is a multiple choices. You can select more than one, so that. But the most of you thought B is the most likely reason, but all options got some votes. Oh, actually, I can share results. Now you can see it. Okay, I just saw that button. Okay, so now we can talk about this. So let's evaluate. I'm not going to tell you the answer to this question immediately. I'm going to lead you through the logical process of how we can tell what is the correct answer to this question. So there's 4 conjectures that is made. Conjectures are just hypotheses. It's a guess of what is happening. And the first guess is that the Earth is closer to the sun in summer and farther away in winter. Is that correct? How can we judge whether this is correct? We need to look at for evidences that support this conjecture or argues against it. So what evidence would support this conjecture? What evidence would argue against this conjecture? Anyone want to type anything in the chat or speak up? Feel free to do so. I don't see any reactions. Is the Earth closer to the sun in summer and farther away in winter? There are some very simple evidences against this conjecture. And what is it? That you know that we live on the northern hemisphere, right? When it is northern hemisphere in the when it is summer in the northern hemisphere, it is winter in the southern hemisphere. Or when it is winter here, it's actually summer in the southern hemisphere, right? So for example, during the time of Christmas, it is cooler cold in the northern hemisphere, but it's actually really hot on the southern hemisphere. So that the northern hemisphere of the Earth and the southern hemisphere have opposite seasons. And this is a very strong argument against conjecture A, right? Conjecture A says that if the Earth is, that we have winter when the Earth is further away from the sun, and we have summer when the Earth is closer to the sun. But that cannot be right if the 2 hemispheres are having opposite seasons, right? So this is the simplest evidence against conjecture A. And I can actually tell you that the Earth is indeed on an elliptical orbit, but we are actually closer to the sun in January than it is in July. Our Earth is actually closer to the sun in January, but we have winter in the northern hemisphere in January. So it cannot be the overall distance of the Earth between the Earth and the sun that determines the season. Oh yeah, this plot actually shows the Earth is actually closer to the sun in January than it is in July. In January, we are about 147 million kilometers away from the sun. In July, it's about 152. Distance cannot be the reason for seasons. And also think about this fact that remember that I talked about the size of the Earth compared to the size of the sun, right? The Earth, when we shrink the sun to the size of a basketball, the Earth is like a tiny grain of rice that is orbiting that basketball about 26 meters away. And so it is actually a very, very tiny. And also the Earth's orbit is very, very circular. And this change in distance is a very, very small amount in compared to the overall distance. This is only a 3% change in distance. It's not going to cause a much change in terms of the temperature. So the conjecture A is certainly incorrect. The Earth is closer to the sun in summer and further away in winter. That is not causing the seasons. Now, what about conjecture B? Most of you chose this conjecture. You said the tilt of the Earth's axis brings one hemisphere closer to the sun than the other hemisphere. So this would solve the problem between of the opposite seasons between the north and the south, right? So you would say, okay, if because the Earth's axis is tilted, then during the northern summer, the northern hemisphere is closer and the southern hemisphere is further away. But on the other one, we go to the other side of the sun, then the northern hemisphere will be further away and southern hemisphere will be closer. Could this be the correct hypothesis? I want to show you two facts that shows that this hypothesis may have some problems. The first fact is that Earth has a slightly elliptical orbit. The Earth is actually 5 million kilometers closer to the sun in January than it is in July. That is about 3% change in distance. And the Earth's radius is about 6,400 kilometers different in size. So see, the orbital distance between January and July is about 5 million kilometers. And the Earth's radius 6,400 kilometers. So which number is bigger? Is 5 million bigger than 6,400? It is much bigger, right? It's almost 1,000 times bigger than the size of the Earth. This is the orbital, the distance, the difference in distance between January and July. It's about 5 million, but the Earth's radius is only 6,400 kilometers. So if you compare the northern hemisphere in July and the northern hemisphere in January and in July, which one is closer to the sun? So when you evaluate the distance between the northern hemisphere and the sun, you need to consider not only the orbit of the Earth, but the orbital distance of the Earth between orbital distance between the Earth and the sun at that time, but also the size of the Earth, right? Because you are saying that if this tilt is causing the distance to be different, and so which part is closer? So I was saying the Earth is 5 million kilometers closer to the sun in January than it is in July. So the center of the Earth is going to be closer to the sun in January by 5 million kilometers. And then if the northern hemisphere in January it is tilted away from the sun, it is 5 million minus 6,400 kilometers, right? Or 5 million plus 6,400 million kilometers. And so it is going to add a tiny bit on that. So it's still roughly 5 million kilometers. But then in July, that it is actually further away by 5 million kilometers. And even if you are tilted toward the sun by 6,400, it's not going to change it very much. So if you compare the northern hemisphere in January and the northern hemisphere in July, we are actually closer to the sun in January than it is in July still. So it's actually much easier to just think about our scaled model. Our scaled model of the solar system is like this. When the sun is shrunk to the size of a basketball, the Earth will be just the size of a grain of rice, orbiting at a distance of 26 meters away. Okay, and the Earth size is so insignificant compared to the, it's so insignificant that the tiny difference between the two hemispheres in their distances to the sun will not cause any noticeable difference in the amount of heat we receive. Because the Earth is so tiny, I mean, that if you compare one side of that grain of rice to another side of the grain of rice, they're essentially at the same distance to this basketball, and it's 26 meters away. Okay, and so that, and the Earth's orbit is indeed not circular, it is a slight elliptical, but that elliptical is very, very close to being circular. The change of that is about 3 and so in 3% of 26 meters is about it's less than a meter, but already that is much bigger than the size of the rise, right? And so that it is indeed causing a slight difference. The distance causes slight difference, but it's actually not the dominant factor in changing the temperature on Earth. There's some other factors that can give you much larger change. The distance is not the same. And especially because the Earth is so tiny, the difference between the northern and southern hemisphere is so small compared to the actual orbital distance to the sun, and they're not going to cause any noticeable difference in the amount of heat we receive. So the second conjecture is also incorrect because the Earth is so tiny, and the northern hemisphere and the southern hemisphere are essentially at the same distance to the sun. Their distance to the sun actually is almost the same, and there's not any difference this can cause to the temperature on Earth. So if distance doesn't matter much here, what factors would matter? So I want to think about one thing is, why is the Earth hot during the day? Why is the temperature high during the day and low at night? You can give me some feedback in the chat window. Yeah, someone said there's sunlight, because there's sunlight. The sunlight is making us hot, and at night we're not being shone by the sun, right? So that you can see the day and night temperature variation can be huge, right? In Hong Kong, it's not that much, but in many other places in the world, day and night temperature can vary by more than 10 degrees or 20 degrees. And so the fact whether the sun is shining on you or not is a much bigger difference that can cause the temperature to change. So, and also I want you to think about, why is the noon hotter than the morning? I mean, in the morning, you also have the sun shining on you. At noon, you have the sun shining on you. Why is the noon hotter than the morning? Please feel free to type in the chat window or speak up. More direct? Direct sunlight. Yeah, at the noon, the sun is shining directly on top of us, right? So it's very high in the sky, and it is shining directly onto us. So it's more direct sunshine. That's correct. But in the morning or in the evening, when the sun is shining from a very, very low in the sky, it is shining at us at a much smaller angle. So it's not very direct. It's shining towards us from an angle. And so that is not, the heating is not so intense. So that is correct. That is one reason why this is one of the reasons that can cause strong temperature variations, that can cause a strong difference in hot versus cold. What about this? Then why is the afternoon hotter than the noon? Usually that the temperature doesn't reach its maximum at noon time, right? You said, okay, the direct sunlight give you a hotter temperature, but in the afternoon, the sun has moved slightly lower in the sky. It's not as high as it is at as the noon. But why is usually the afternoon hotter than the noon? Someone said heat radiation. Shui said heat radiation from ground. So yeah, you can say so, because that the sun is heating up the ground, right? The sun has been shining, the Earth retained the heat, that's right. So because the sun has been shining for longer periods of time, and so the ground becomes hotter, and that keeps that radiation so that we can feel hot for a while afterwards, after the sun goes away. So that even after sunset, it doesn't cool down immediately. So for example, on a hot summer day, that it was really hot during the day, and right after sunset, you don't immediately feel it is cool. You still feel it is really warm and hot for a long time. And especially in the summer days, that you have to wait until very late into the evening for it to start to cool down, because the heat doesn't goes away immediately, right? That's exactly right. So and what is happening is because of the not only the ground but also the atmosphere, the air can keep those heat around, and so that when if the air has already been heated, we can feel that heat for a long time after the sunshine goes away. And so both the direction of sunshine and the duration of sunshine are much stronger heating effects than distances. So the first fact that the noon is hotter than the morning, that is because the sun is shining more direct. And for the second question, why is the afternoon hotter than the noon? It's because that in the afternoon, you have had the sun for longer periods of time than what you had for the noon, right? At noon, you have only had the sun shining for 6 hours, but in afternoons, you can have it shining for 8 hours or 10 hours. And so that longer periods of sunshine accumulates that heat, and so that you feel the temperature to be hotter. So the duration of sunshine is also a very strong heating effect than the distances. So you can see that in this poll, the option C says the sun's rays strike the Earth more directly in the summer and cause more heating. And this is one of the correct reasons. And D says the tilt of the Earth's axis causes the days to be longer in summer. Indeed, right? The daytime is longer during the summer than it is during the winter, so that we have longer periods of sunshine. So this is also a reason why summer is hot than winter. So both C and D are correct. Both are ultimately caused by the tilt of the Earth's spinning axis. And so why is the sun shines towards the Earth more directly in summer? That is because the axis is tilted toward the sun during the summer. So here is a diagram showing that. The Earth's axis of rotation is tilted by 23.5 degrees. So if here is the sun and here is the Earth, this is the rotation axis of the Earth, and this is pointing towards the North Celestial Pole. And you can see in this picture, the sun is shining towards the southern hemisphere. Actually, let's use this bottom picture to explain this. This rotation axis of the Earth stays fixed, almost fixed in space. It doesn't wobble that much, right? I was saying that it was wobbling, but that wobbling motion, it took 26,000 years to finish one round. But so over the time scale of a year, it basically pointing at essentially the same position and pointing towards the North Star. So it always points towards the North Star during the year, and it stays fixed. So when we are on this part of the orbit, there's music in your background. There is no music in my background. Do you hear anything? Actually, maybe it was the YouTube video. Oh, I paused it. I don't think that should be fine. Okay, sorry about that. Share screen again. So let's look at this plot. So the sun is here, this is Earth, and the north rotation axis is pointing towards the North Celestial Pole. And on June 21st, the sun is shining directly towards the northern hemisphere because the pole is tilted towards the sun on this part of the orbit, so that the sunshine is more direct, very strongly directed towards the northern hemisphere, so that in the northern hemisphere, we see the sun to be higher in the sky. And so that because it is higher in the sky, the more direct sunshine gave us more heating. But in December, the North Pole is still pointing that same direction, but this time the northern hemisphere is at the sunshine coming towards the northern hemisphere is at a larger angle towards the ground, so that is giving it less direct heating. And the reason that more direct heating give you more heat is because that if the sun is higher in the sky, the same amount of light is concentrated to a smaller area. So here, see here, this is let's make a cardboard and then dig a hole in the middle and then let sunshine shine through it. And you can see if the sunshine is higher in the sky, this amount of heat is concentrated to a smaller area. But if the sunshine is coming from lower in the sky, the same amount of heat that penetrates through this cardboard is going to be spread over a much larger area, right? So the same amount of heat it is spread over a larger area, then per unit area, you will get a lot less heating. So this is because the sun strikes the ground more perpendicular. When it strikes the ground more perpendicular, then you will have more intense heating. But if it is struck it at an angle, then you will have less amount of heating. So that is the reason for what I was saying. The first reason why we have more intense heating during the summer and less intense heating during winter. But there's a second reason. The second reason is the time, the duration of sunshine. In summer, we have much longer daytime, and in winter, we have much shorter daytime. Here is a picture showing the tracks of the sun throughout the year using a pinhole camera. So this is taken in England. That they use the pinhole camera, and basically it's a camera with a very, very tiny pinhole in front. And so it can allow in very little light at a time, and either keep exposing this whole thing for a year, and then they were able to trace out the tracks of the sun throughout the sky for the whole year. You can see here, this is the track of the sun in December. Here is the tracks of the sun in June. You can see in June time, the sun reach a much higher altitude in the sky. In December, it is very low in the sky. This is for England. They are at much higher latitude, so the sun is not as high as we can see in Hong Kong. And also that you can see, because the sun is, when it is very low in the sky, in winter, it actually remains above horizon for shorter amount of time. But in summer days, that you have the sun above the sky, above the horizon for much longer periods of time, and this give you more heating, and so that it give you longer periods of heating. So that is causing the temperature to be hot. And here is a figure showing why the duration or the sun, I was showing the same thing again. So this is again about the direction of sunshine. So in this picture, the left one shows you the situation on June 21st. The right one shows you the situation on December 22nd. The sun, you can think of the sun in the middle, so that this is two positions of the Earth on its orbit. And when the Earth is on the left side of the sun, so the sunshine coming from here, it is almost directly towards the northern hemisphere. So for northern hemisphere, you get more direct sunshine. And for the southern hemisphere, the sunshine is pointed directly towards the southern hemisphere. in December, so that for the northern hemisphere, you are receiving the sunshine at a much larger angle, and so that you receive a lot less intense heating. And then also the summer days are longer because of the tilt of the Earth's rotation axis. What determines the length of the day and length of the night? And there is this division on the Earth that the part of the half of the Earth that is shined by the sun is during the daytime. The half of the Earth is not shined by the sun is at night, right? And when the North Pole, when the rotation axis of the Earth is pointed towards the sun, for the northern hemisphere, we have more than half of the day spent on the day side, and less than half of the 24 hours spent on the night side, because this line that is perpendicular to the orbital plane of the Earth is determining which side of the Earth is bright and which side of the Earth is dark, right? And because this whole half is bright, so if we are at the Tropic of Cancer, we are at 23.5 degree northern latitude, then we would spend more than 12 hours. You can see that for this line, more than half of it is on the day side. And this means that we would spend more than 12 hours on the sunny side, on the bright side, so that we have more than 12 hours of sunshine. But in winter, on December 22nd, the day-night line will be like this, and the rotation axis is pointing away from the sun. Here, this time, the sun is coming from this angle. You can see we have less than half of this line spent on the bright side of the Earth. So this is so that we have less than 12 hours of sunshine on December 22nd. So for Hong Kong, it's very close to the 23.5 degree. We are at 22.5 degree. So on June 21st, we can have almost the sun shining directly overhead of us. But in December, it is going to shine at us at a very small angle. And the different length of the day is the second reason for season. So there are two reasons, but both of them are caused by the rotation axis of the Earth, because the Earth's rotation axis is tilted. So in summer, the northern hemisphere receive more direct sunshine, and it receive more than 12 hours. In winter, it receive less direct sunshine and receive less than 12 hours of sunshine. And so that these two reasons combined give you the huge temperature difference between summer and winter. So now you can see that why do we have seasons? The distance is not the factor that matters here. Certainly the first factor is not correct because the southern and northern hemisphere have opposite seasons. But even the second option is also incorrect. It is wrong reason. Both of these are wrong because Earth is so tiny compared to the distance to the sun. The two ends of the Earth are essentially at the same distance to the sun. That distance is not causing any change in our temperatures. What causing the change is the direction of sunshine and the duration of sunshine. So the days is longer and the sunshine is more direct. And also we have some special days during the year. So as I was saying, there's two special days. June 21st, this is the summer solstice. This is sun is at its farthest point north of the celestial equator. It gives you the longest day of the year for the northern hemisphere. This is all for the northern hemisphere. So, and then winter solstice is the opposite, that December 22nd, the sun is at its farthest point south of the celestial equator, and you have shortest day of the year. And also there's two special days in the spring and in autumn. So that in autumn equinox, this is September 23rd. the sun is directly shining on the celestial equator at this position. And at that point that we receive equal amount of sunshine from the north and the south, so that both the northern and southern hemisphere receive about the same amount of heating. And also the day and night are both 12 hours for everywhere on Earth. And so that is why we call it equinox, because on that day, everyone receive the same amount of daytime hours. So that is why we call it equinox. And also on March 21st, it's exactly the same thing. The sun is also on the celestial equator, and it's you get equal day and nighttime, daytime and nighttime, both 12 hours. So that is are the special days of the year, and so that concludes the reason for seasons. I hope that is clear. Any questions for me? Good. Now I think we should take a short 5 minutes break, and then we'll come back at 3:30, please. Okay? And then we'll resume in 5 minutes. Thank you. Okay, let's resume. As we decided last time, we want to take a shorter break so that we can end earlier. I hope I can end on time today. So we have talked about the reasons for seasons, and now let's talk about why we have phases of the moon. So here are some pictures of the moon. Sometimes we can see the moon as a full moon, as a full circle. So we call that the full moon. And sometimes we can see just a silver crescent of the moon. And we call that the crescent moon. Sometimes it's just a very tiny silver lining. And sometimes we see the moon being half a circle, and we call that half moon. So why we have why the moon sometimes is a full circle, sometimes half, sometimes just a silver crescent? What is the reason for the moon phases? First of all, before I ask you that question, I want to ask this question: why does the moon shine? Is that because it radiates or because it reflects sunlight? Actually, let me start the next poll. Okay. That's a simple question. That is a simple question, right? Is that because it radiates or because it reflects sunlight? Okay, it is very obvious. I think all of you are getting it correctly. So I'm going to end the poll now. Sorry for those who you haven't got a chance to respond, but no one misses this. So the reason oh, did I just show the answer on my slide? Okay. Why does the moon shine? It's not because it radiates optical light. It is because it reflects sunlight. It is reflecting the light from the sun. So now then let me ask, why does the moon sometimes look like a full circle and other times a crescent or partially lit? Oops, I should not do that. Let's go to the pole directly and launch this pole. Why does the moon sometimes look like a full circle and other times a crescent? Is it because of the shadows or because of the sunlit side of the moon is partially facing away from us? Okay, I see an even split among you. Among you, we see an even split. Half of people say it's because of the shadow. Oh, now the shadow hypothesis is winning. Okay, I'm going to end the poll now and share the results with you. So more than half of you said it is because the Earth's shadow is cast on the moon. When the Earth's shadow is cast on the moon, different phases occur. And the other, a smaller number of you said when the sunlit side of the moon is partially facing away from us, different phases occur. So which one is the reason? Let's take a look. So here are all the different pictures showing the phases of the moon. The phase of the moon actually changes continuously over the whole month. It takes about 30, almost 30 days for it to repeat one cycle. So here at the beginning of the month, you have, or at the beginning of a lunar month, of course, it's not always aligned with our calendar months. So let's just say that we start with the silver lining on the right-hand side, and then you see this part gets bigger and bigger until it becomes roughly half. In this picture, it's exactly one half of the moon that is bright and one half is dark. And then it gets bigger and bigger and become a full circle in the middle of the month. And then it gets smaller again. Part of it gets it starts to disappear on the right hand side, and it eventually becomes one half again at this time, and then the silver lining is shown on the left hand side. So they see it start with the silver lining on the right and then ends with the silver lining on the left. So is this actually caused by the shadow of the Earth? Can the shadow conjecture work? Is it, if it is because of the shadow of the Earth, you know that the Earth is round, right? If the Earth is round, then the shadow of the Earth should also be a circle in space, right? So we have a big shadow cone that is going to have a shape of a circle. And if the Earth is happen to be in our shadow, then yeah, it should give you something like this. But will this hypothesis work to reproduce these other phases of the moon? And you may say, okay, this one, it looks like maybe this is part of a larger circle. But how about this one? How can it be a straight line? How can the Earth's radius, the shadow cast a straight line on it? And what about this? This is not even part of a circle that, I mean, if it is part of a circle, it is on the bright side, but not on the dark side, right? So we try to draw a circle to mimic the dark side of this. How can we fit it? I mean, you certainly cannot put a circle on there to match this envelope between the bright side and the dark side of the moon, right? This will not work. The shadow of the Earth certainly cannot produce these kind of moon phases, right? It may be able to do this too, but certainly it cannot do the other three. So it cannot produce Earth shadow cannot be the case. Earth shadow cannot cast, say, this kind of shape on the moon. The shadow will not produce, will not produce the faces we see. What about other evidence? We also have other evidence. Quite often we see a crescent moon at sunset. And I think you probably have experienced seeing this before. When you go out to see sunset, sometimes you see the moon is very close, just above the horizon, and you see a silver lining of it. It's really beautiful. And when we see this, where is the sun in this picture? The sun is just setting, right? The sun is just below horizon. And if you try to measure the angle between the moon and the sun at the time, and maybe it's something like this. It's not always 25 degrees, okay? It can be larger and or smaller, but it is an angle that is smaller than 90 degrees. So if you think about this in space, that the sun is in this direction in space, and the moon is at this direction. And if we go looking from the Earth's perspective, if we think about these three things are just three objects in space, and if you connect a line between the moon and the Earth, and you connect another line between the sun and the Earth, and these two lines form an angle that is about 25 degrees, let's just say, okay? For example, this measurement is 25 degrees, and then the direction towards the moon and the direction toward the sun is only separated by 25 degrees. That means the moon and the sun is in the same, roughly in the same direction as the Earth. Where is the shadow of the Earth? The shadow of the Earth is behind us, right? If the sun is in the west, the shadow of the Earth will be in the east, right? And how can the Earth cast a shadow on the moon at that time? No, it cannot be cast a shadow on the moon at that time when the moon is also in the west, right? So this phases of the moon cannot be caused by the shadow of the Earth. That hypothesis is just incorrect. It's not caused by the Earth's shadow casting on the moon that causes different phases. When the Earth's shadow is cast on the moon, that is that we have a lunar eclipse. And that does happen occasionally, but happens very, very rarely. And that is what we call lunar eclipse, but it's not what causing the different phases of the moon that repeats every month. What repeats every month is the lunar phases, and this is caused by the sunlit side of the moon partially facing away from us, and then different phases occur. And this picture shows you why that is happening. The sun is actually very far away from us, much further from Earth than the moon is. The moon goes around the Earth, and the Earth goes around the sun on a much larger circle. So we can just think of the sun shining towards us from a distance. So you can think of this as a beam of light that is parallel. And so if you have the Earth here, one half of the Earth is bright because this half is shined by the sun. So we have daytime on this side of the Earth and nighttime on that side of the Earth. And the moon is going around the Earth, right? And half of the moon is always bright because the moon is always having half of it facing toward the sun and half of it facing away from the sun. So if you talk about daytime and nighttime on the moon, you know, okay, this side of the moon is during the day and this side of the moon is at night, right? So everything in space, in our solar system, every object in our solar system will have half of it being illuminated by the sun and half of it being dark. And why it is dark, it's just because it doesn't radiate visible light, so we cannot see anything coming from it. So in this picture, we actually draw it so that you can see there's a darker half, but in space, because the darker half is not shined by the sun, it doesn't reflect anything, And so we're not seeing any light from it. So we really cannot see this darker half in space. And so when the moon is at different places on its orbit, we actually see these different phases. So you need to imagine that how we can see these phases. So what you can imagine that there's a person standing on Earth looking towards these different directions. And then these pictures on the outer circle of this diagram shows you what that person would be seeing. For example, if the sun is shining from this direction and the moon is in roughly the same direction, okay? And in this place, we cannot see any part of the part that is bright. We can only see the darker half of the moon. And because the darker half doesn't emit visible light, we just don't see the moon at all. The moon is completely dark, and you don't really see it at night. And so this is what we call the new moon. And then when it is moving slightly away from the direction of the sun, for example, when the moon is over here, this half is facing the sun, this half is bright, this half is facing away, so this half is dark. And you have a person that is looking towards this direction on Earth, and if you're standing on Earth somewhere and looking towards this direction of the moon, what will we see? So you can see here, there's a little dashed line on the slide, and this represents which part of the moon that a person on Earth can see, right? You can see most of this part is going to be dark, and you may be able to see a little bit of this bright side. And that is why we have a crescent moon, that you have less than half of it being illuminated. It's not that the moon is only illuminated by this much. The moon is illuminated, half of the moon is illuminated by the sun, but we cannot see that whole half. We can only see a tiny fraction of that illuminated side. We can only see a tiny fraction of the sunlit side of the moon. And then when the moon goes to this position, half of it will be able to be seen by a person on Earth, right? Half of the bright side. So you can see that this is, again, this side is bright and this side is dark. And this dashed line represents which part we can see on Earth. We will see one half of it being dark and one half of it being bright. So this is what we are going to see. We see a half moon, a half circle. And we call this the first quarter because this is 1/4 of a month. This is 1/4 of one round of rotation of the Earth, of the moon going around the Earth. So the moon goes around the Earth. This is one round. One round is 360 degrees, and 1/4 of 360 degrees is 90 degrees. So that is at this position we call it 1/4. We call it a first quarter moon. And this one is smaller than half, we call it crescent moon. And when it is bigger than half on this place, so you can see if it is over here, the person standing on Earth looking towards the moon, you will see more than half of the moon being bright and a tiny fraction being dark. And so that on Earth, you would see this kind of shape. It's more than half of a circle, but not the full circle yet. And we call that a gibbous moon. Gibbous meaning more than half. And then if the moon is over here, is in the opposite direction away from the sun, you would see that from the Earth's perspective, you will see the whole moon. You will see the complete side that is illuminated by the sun. So the one half of the moon is illuminated by the sun again, but we can see that complete half. So while from the Earth's perspective, you see a full moon. And then in the bottom half of the circle, we repeat the same process as above, but this time the fraction that is illuminated gets smaller and smaller. The fraction of the illuminated side that we can see gets smaller and smaller. At this position, we see more than half. At this position, we see half of it. At this position, we see less than half of it. So we have gibbous moon here, And then this is called the third quarter moon because it's 3/4 of a month. So this is called the third quarter moon. And here is a crescent moon again. So when it is less than half, we call it crescent. When it is more than half, we call it gibbous. And also that you see some words called waxing crescent and waxing gibbous. What does waxing mean? Waxing means it is increasing with time. So that I think in the first half of the month, going from new moon to a crescent to first quarter to gibbous and fall, you see the fraction of the illuminated side that we can see gets bigger and bigger. It goes from 0% to less than 50% to 50% to more than 50% to 100%. Right, this fraction is getting larger and larger, so that we call it waxing. So this is waxing crescent and this is waxing gibbous. But on the second half of the month, this is called waning gibbous. This is a gibbous moon, just like that. You can see this is symmetric to each other, but you have a different side that is illuminated, and the side that is illuminated gets smaller and smaller with time towards the new moon. So we call it waning. Waning means it's getting weaker and weaker or getting smaller and smaller. So the fraction of the illuminated side is getting smaller and smaller. And so this is what we call waning gibbous and third quarter and the waning crescent. So these are the different names for the different moon phases. Okay. Actually, I explained this slide already. Basically, this is new moon, this is first quarter, full moon, and third quarter. And waxing crescent, waxing gibbous, waning gibbous, and waning crescent. Want to emphasize again that this is the inner circle in this diagram is the orbit of the moon around the Earth, and these pictures on the outside hand side, on the outer side circle, this is what we can see, the image we would see from the perspective of the Earth. Okay, this is the image we will see in the sky. Okay, and that is the fourth circle, and we have waxing crescent for the first 6 or 7 days, and then you have the first quarter moon with 1/2, and then you have waxing gibbous, and then you have full moon, and then waning gibbous, third quarter moon, waning crescent, and then new moon. So we always use the date on which that we cannot see the moon as the start of the lunar calendar month. Lunar month. So lunar month, we always start with new moon and ends with new moon as well. So I want to talk about some questions, give you some questions and see how well you understand this. So when we see a full moon on Earth, where is the moon on its orbit in the following diagram? A, B, C, D, or E? I'm going to start this poll again. See if you have understand what I'm talking about. So the order in my poll is corresponding to directly to these. So you can just use A, B, C, D to judge which one is the one you want to choose. Okay, very quickly. All of you who answered have chosen the right answer. The correct answer is A. I'm just going to end the poll now. Oh, I guess there is one wrong answer coming in. You need to act quickly or make your best guess quickly. So this position is when we see the full moon. Certainly not the E position. So this is a position that is on the opposite side away from the sun. On Earth, we would see the complete half that is illuminated. So we see a full moon, we see a full circle, right? So This is the position of the full moon. And where will we see a crescent moon, A, B, C, D, or E? I'm going to show you the poll again. Orbital position of the crescent moon, the answers are given in the same order as well. I'm going to wait a little bit for those who are hesitating to answer. Okay, most of you got it correct. And most of you answered D. Answer, this is the position when you see a crescent moon. And one of you answered E, on the side of the orbit toward the sun. I guess maybe that was my problem, that that option wasn't phrased properly. So you would see a crescent moon over this area or this area, right? The bottom half would also give you a crescent moon, but not at the position of E, because at this position you will only see a new moon, or you will not see a moon at all. So it doesn't have to be 45 degrees. I would just say that anywhere between 0 degrees and 45 degrees away from the sun, you will see a crescent moon. So this is the correct answer. Here is a harder question. When does the third quarter moon first rise? And let me give that a try to see if you can figure this one out. This is, so now you not only have to think about where is the third quarter moon. Actually, this picture gives you what is the third quarter moon. But you also have to think about, when do you see the third quarter moon on Earth? Right? Do you see it at noon? Do you see it around 6 p.m. in the evening, or at midnight, or at 6 a.m. in the evening? And when do you see it rising above the horizon? You have to think about where you are on Earth that you can see the third quarter moon rising above the horizon. This is a difficult question, I'm saying, okay? So if you have no clue how to do it, don't worry about it. I'll explain in a minute. Okay. I'm going to end the poll now, and I'm going to show you the results. You guys are pretty evenly split between the B, C, and D, around 6 p.m., midnight, or around 6 a.m. When do we see a third quarter moon? So how can we think about these kind of questions? So to figure this out, we need to think about our horizons. Sort of, where is our horizon? Where are we on Earth when we can see that moon at that place, at a certain phase moon at a certain place? So you have to draw a diagram like this, or a diagram like the previous one. In this one, I chose this picture because it shows the North Pole of the Earth. And you see here is the the ice cap, the Arctic Ocean, and the ice at the Arctic Ocean. So this is the Earth, and if we are looking down on Earth from above the North Pole, the Earth rotates in a counterclockwise direction. Okay, and here in this figure I'm placing the sun on the left hand side, and this is the orbit of the Earth, and this is the orbit of the Moon. The Moon goes around the sun. The Moon goes around the Earth, and the Earth goes around the sun. And in this picture, the Earth goes around in the counterclockwise direction. So in all of the pictures I'm showing, we are going to assume that we are looking down on Earth from above the North Pole, and so that we know which direction is sunrise and which direction is sunset. And so let's consider a simple case that someone standing on the equator at noon. Which side of the Earth is during the day? This side is during the day, right? So that if it's what time is noon is that when the sun is directly above your head, and this is that person standing this time. If you're on this side of the Earth and directly facing toward the sun, this is at noontime. And midnight will be on the opposite side, right? And then you can also draw the horizon of this person, and so you can draw a line that is tangent to the circle. So this is the horizon of the person, so that for anything on this side in the space, that this person can see it above his or her horizon, but this side that person cannot see. So this is the horizon. And because the Earth is so tiny in space compared to the size of things, the orbits of things, this picture is really not drawn to scale. And we can just think of it actually very, very small, and we can extend the horizon to infinity. So we can actually just draw the horizon directly through the center of the Earth. It's going to be the same thing. Just for convenience sake, I just draw the horizon like this. And then because the Earth always rotates from west to east, and since we define the Earth's rotation to be counterclockwise in this picture, so then this side of the horizon is west, and this side of the horizon is east. And as we rotate this horizon will rotate with us and going in this direction, right? Okay, here I'm letting it rotate. And you can see this is, as the Earth spins around, this is how we are seeing different parts of the sky, right? And that was why the stars you see at night will depend on what time of the day you are at. And because we are spinning, we can also see things rising in the east and setting in the west. Because you can see when we are doing this, from our perspective, the sun is setting in the west and rising in the east, right? So it rises from below horizon to above horizon just now. And you can see here, now the sun is setting for this person. And now this is night. And now it is, sun is rising for this person. And now it is noon again, right? So this is how you can figure out what time of the night it is and where, according to where you are on Earth. Yeah. So you want to figure out this. We let the so here you see that this is the time of sunset. The sun is moving from above your horizon to below your horizon, right? So when we are moving this way, from our perspective, the sun is going in the other direction, right? So it's going from above horizon to below horizon. So it is the sunset time because the horizon is moving this way. And now this time is midnight. We are directly on the opposite side away from the sun. This is midnight. And then this is sunrise, so that the sun is rising from below horizon to above horizon, so that is sunrise. and this is noon. It's directly overhead. So if we draw the sun on the other side, it's really the same thing. It doesn't matter where we draw the sun. Just remember that the side of the Earth or the moon that is facing the sun is the illuminated side. It's again, we will need to draw them. The Earth and the horizon is going to rotate in counterclockwise direction, and we're looking down on Earth from above the North Pole. So now we can try to figure out when do we see the third quarter moon rising, right? So third quarter moon is over here. Let me see is over here. When is it rising? This time is when the third quarter moon is rising, right? It's because that when the horizon rotates into this angle, the third quarter moon is going from below horizon to above horizon. This is the time when it rises from below to above, so it is the time when it is rising. So you would on Earth you would see the third quarter moon rising if our horizon is placed at this position relative to the sun. And what time is it for this person when it is seeing this? It's directly opposite to the direction of the sun, right? So this is midnight for that person. So this is, again, when does the first quarter moon first rise? Is this correct? That the moon has to be on the horizon for that to happen, right? This is not the time. The third quarter moon is over here because the horizon is moving in the counterclockwise, rotating in the counterclockwise direction. It's actually going from above to below. This is the time when third quarter moon is setting. And if you choose the other side, that this is when the third quarter moon is rising above the horizon. So you can see it is rising above horizon. And so this is the time, the orientation of the horizon when you can see the third quarter moon rising. And for this position, it is midnight for this person because it's on the side that is direct facing away from the sun. So what time is it? Where is the sun? The sun is directly below the horizon. It has to be midnight for this person. So the option C is the correct answer. Okay, now I have a few simple questions, and let's try to finish these simple questions, and then I'll ask you some of the more harder questions next time. Let's see. Stop sharing the results. When you see the crescent moon at sunset, where is the moon on its orbit in the following diagram? Is it A, B, C, or D? Remember, there's two crescent moon in this circle, right? In two positions, you have a crescent moon among these. Which one is the one that we'll see on sunset? So you need to think about where is the crescent moon first, and then think about where the horizon is at sunset. And then you can see which moon you can see, which crescent moon you can see. Okay, and it is the poll, and I can share with you the results. That is not looking good. So again, we are looking at, I mean, in all these diagrams, we are assuming we are looking down on Earth from above the North Pole, right? And here is let's try to analyze this. And you can see here the sun is shining from this direction. Where are the crescent moons? The crescent moons are one we see less than half of the illuminated side. So that you can see these are the positions of the crescent moon. That, I mean, because from when the moon is, the half of the moon that is illuminated is always the half that is toward the sun. And for this position and this position, we can see mostly the dark side, not the illuminated side. But we can only see a tiny fraction of the illuminated side. So this is the positions of crescent moon. This is a waxing crescent. This is waning crescent. Those two positions will give you gibbous moons, because in those two positions, you would see more than half of the illuminated side. You will see, I mean, the illuminated side will be more than half of the moon, right? As you can see from the perspective of the Earth. So these would give you a moon that is bigger than 1/2 of a circle. And these places will give you a moon that is less than 1/2 of a circle. So these places are crescent moons. And now we need to decide, so this is B or C, right? It certainly cannot be A. Now we need to decide which one of these is the one that we can see after sunset. So where is sunset? So we need to draw the horizon. When the sunset is happening, it is either on the, I mean, it has to be on the horizon, right? Because the sun is going down from above horizon to below horizon. So it is crossing the horizon. So the horizon is aligned with the direction towards the sun. And it has to be in the west, so that this side is west. And that means the person is standing on this side of the earth. And the sun is in the west, is going below the horizon. And for this person, which of these crescent moon can this person see? It can only see this crescent moon, not that one, right? So the correct answer is B, not C. So the correct answer to that question is B. So this was the previous one. Okay, that one. Now another question: in which direction will we see a full moon at sunset? We launch the poll. You can also borrow from your experience to answer these kind of questions. When do you see a full moon at sunset? Where usually which direction it is at? So you may have seen this on the Mid-Autumn Festival times. So again, this is sunset, and then so which direction is the horizon? And so where is the full moon on that horizon? Okay, so time is limited. So majority of you got it correct. And the correct answer is A. So this is how you can draw this, right? So this, when it is sunset, again, that horizon is aligned with the sun, and it is in the west. And where is the full moon? The full moon is over here, so it is in the east direction. So correct answer is A. So that is the correct answer. Okay, can you see a full moon during the day? The very last one. Okay, I promise this is the last question now. Okay. And the correct answer is C. Can only see it as sunrise or sunset. And sorry, so I didn't draw the horizon, but you either have to draw so if you want to see the full moon during the day, that means it has to be during the day, and also you can see the full moon. That means the full moon has to be above the horizon, so that the horizon has to be facing somewhere towards this direction. But then that will be night, right, for that person. So that the only time when both the full moon and the sun is above horizon is at sunrise or sunset, because the full moon is in the direction that is opposite to the sun. You have to, if you want to see the full moon, the full moon has to be above horizon. You want to see it during the day, that means the sun has to be above horizon. But the sun and the moon are at the opposite direction. So the only time you see it is when the horizon is aligned with the direction connecting the moon and the sun. So that is only at sunrise and sunset. The correct answer is C. Okay, so now that's the end of today's lecture. Thank you very much. We'll continue to talk about these kind of things next time and talk about lunar and solar eclipses as well. Thank you very much for joining today. See you. Have a good evening.